All right, here are the rest of your probability notes. We already did this page in the back of it. All right, so now we're going to be working on theoretical probability. What we did so far was all experimental probability. We actually did an experiment. All right. Some of the things you have to know what the sample space is, and that's just all the possible outcomes. And make sure that all the outcomes are equally likely outcomes. That makes it a fair thing. All right, theoretical probability. All right, if the sample space has n equally likely outcomes and event A occurs in m of these outcomes, then the theoretical probability of an event is the probability of A is m over n. All right, so the probability of A is equal to the number of times A happens over the total number of outcomes. All right, and that's just with theoretical probability. So again, this is in theory. We're not doing an experiment on this. We're just saying, well, in theory, what should happen here? All right. So, example 3. What's the theoretical probability of rolling a 3 on a single die? So we're taking one die and rolling a 3. So the probability that you will roll a 3 is, well, there's 1 3 over 6 possible choices. And that's the theoretical probability, 1 out of 6, right? So what's the theoretical probability of getting the sum of 6 on a single roll of 2 dice? All right, so now we have 2 dice this time. All right, so we want the sum of 6. All right, so the probability of the sum of 6. All right, so now what we got to do is that we have to really look at both the dice. All right, so the way you do this is you write die 1, and these are the outcomes. So for die 1, possible outcomes are 1, 2, 3, 4, 5, and 6. And then we have die 2, and the possible outcomes if die 1's a 1 is 1, 2, 3, 4, 5, 6. If you roll a 2, 1, 2, 3, 4, 5, 6, and you roll any number, die 2 can come out 1, 2, 3, 4, 5, or 6. All right, so these are our rolls, our possible rolls, and we can do the easy part first, is the number of outcomes. Well, we have 6 things, and we have 6 rows, 6 columns, so 6 times 6 is 36. So you have 36 different things that can occur. All right. So now we got to figure out which are the ones that we want. All right. The one that we want are the sum of 6. So if we roll a 1, we could roll a 5. So that's 1. If we roll a 2, we could roll a 4. That's another one. A 3, we could roll a 3. A 4, a 2, a 5, a 1, and if we roll a 6, we can't get the sum of 6, so none. So we have 1, 2, 3, 4, 5. So the probability that you will get the sum of 6 is 5 out of 36. And again, you can change this to a percent to write your answer. If you want to change it to a percent, all you have to do is divide. You'll get a decimal. And we can change it to a percent. So if I divide 5 divided by 36, gives me 0.138 Yeah, 138, which is approximately 14%. All right, and I'll take it either way, as a reduced fraction or as a percent. All right, so then we got 2 U-tries for you to do. All right. All right, now combinatorics. All right, combinatorics. This is when you're using the fundamental counting principle or permutations or combinations to find all the equally likely outcomes. All right, so what's the theoretical probability of getting dealt exactly 2 sevens in a 5-card hand from a standard 52 deck? All right, so we want to know what the probability of getting exactly 2 sevens. All right, so the first thing we got to get is our 2 sevens. And the order we get them in doesn't matter. All right, so since the order doesn't matter, we're going to be using C. Okay, not P, we're going to use C. So we're using combinations. All right, so in the deck, there are 4 sevens. And we want to get 2 of them. All right, so that's given us our 2 sevens. There's 4, we want to get 2 of them. All right, so that's our 2 sevens. All right, now we're getting 5 cards total, so we need 3 more cards. And we need no sevens. All right, so 3 more cards, but none of them can be sevens. So we got to get rid of the sevens, and there were 4 of them, so that means 52 minus 4 gives us 48. All right, so there's 48 cards to choose from, and again we're using C because order doesn't matter, and we want 3 of those. All right, so this gives me 2 sevens, this gives me my other 3 cards that aren't sevens, all right, and then that's over in what way I can get any 5 cards. So 52, C, 5. Okay? So now we're going to figure this out using the calculator. So using the calculator we can do C and P. So I'm going to clear this out and we're going to do 4 C, which is under math, under probability. You see we have the C and the P. So C, 2, and enter, and that gives me a 6. So 4C2 is 6. All right, times, then I got to do 48C3. So 48 under the math, again the probability, C, and I want 3. All right, so that's 17,000. Whoops, I should use screen. 17,296. All right, and then that is over 52C5. So now I got to do 52 C5. And that is 2598960. All right, so now we put that all together in the calculator. All right, so I just get an answer and we'll put that all together. So I'm going to do 6. Let me do it this way. I'm going to do parenthesis. 6 times 17296 divided by second and answer. All right, and that gives me 0.0399, which rounded again to the nearest whole percent would be 4%. So I got a 4% chance of getting dealt exactly 2 sevens. All right, you got 2 U tries. Go ahead and do those 2 U tries. And again, I'll give you the answers if you want the answers. All right. So this next one, this is geometric probability. All right, geometric probability. All right, so you have a rectangular area of the batter's strike zone is 15 inches by 20 inches tall. So we have the batter's strike zone, and it's 15 inches by 20 inches. All right, what's the probability that a randomly thrown ball from a pitching machine is high inside strike? All right, the high inside strike would be a rectangular area that's 4 inches wide by 5 inches wide. All right, high and inside means closest to the batter, so the batter would be right here. All right, so closest to the batter and high, so it would be this area right here. So 5 inches by 4 inches. All right, so we want to know the probability that the ball hits that area. All right, so that would be the same as the probability of a high inside strike is the area of high inside strike over the area of strike zone. All right, so the probability of high inside strike is equal to the area of the high inside strike, which it's a rectangle, so the area is 4 times 5, over the area of the strike zone, which is 15 by 20. So again, it's a rectangle, so 15 times 20. You can just multiply it out and reduce it. We got 4 times 5, which is 20, over 15 times 20. And you'll notice the 20s cancel out. So it's 1 over 15. And again, we can find out what the percentage of that is. 1 divided by 15. And we get 0.06. Repeating. So it's going to be approximately 7%. All right, so 7% chance of that happening. All right. I'll do one more of those because this first one, yeah, I'll do one more. I'll do the first you try. Right, if you're dropping a coin into a big circle with a radius of 10 inches, what's the probability that it land in a smaller red circle inside the big red circle, or the big circle? All right, so we have a big circle, and then we have a red circle on the inside, but I don't have red, so I'll use green. So we have a smaller circle in here, and we're going to drop a coin on here, and we want the probability that it lands in this one, which has a radius of 2 inches, and then this big circle has a radius of 10 inches. All right. So the probability that it lands in a small circle is the area of small circle over area of big circle. So we got area of small circle. Well, the area of a circle is pi r squared, so it's going to be pi times 2 squared. Area of the big circle, pi 10 squared. And the pi's cancel out, so it's going to be 2 squared, which is 4, over 10 squared, which is 100, which reduces to 1 out of 20. So you can give it to me as 1 out of 20, or it's 4%. All right, so you can give me either one of those answers, 1 out of 20 or 4%. And that's it for your probability notes.